Hello and welcome to Civil Engineering 3305 again, and the topic of this video and some subsequent ones is the general topic of open channel flow. In this video we're going to define an open channel, define uniform and non-uniform flow, compute some hydraulic elements. Those will make sense in a little bit when I tell you what they are. And compute discharge from slope area method. Now the video might get broken up into a couple of parts to facilitate uploading and timing. An open channel is a conduit whose upper boundary of flow is a free surface. Implicit in the definition is that the dimensions of the channel are such that its length in the direction of average flow is quite a bit larger than either its width or its depth. So for instance, rivers are open channels, streams, sewer networks to some extent, but a tidally influenced bay like Yada Bay or Galveston Bay is not open channel in the context discussed here. It would require different analytical techniques to describe its behavior. It has a free surface and it's influenced by flows just like open channels, but it has multiple flow dimensions at any instant, whereas in open channel flow, as our book discusses it in this chapter, generally the direction of flow is known and it's unidirectional, so it kind of follows that Bernoulli path line definition earlier in the textbook. A couple of notable examples of open channels. I'm just going to sketch two of them, so these are elevation views. The leftmost one is a sewer pipe, and a drainage creek. Okay, so important in the concept is the existence of a free surface. So here we are in drainage. There's the free surface, and if we were to draw the hydraulic grade line, it turns out that the hydraulic grade line is coincidental with the free surface. So there's the hydraulic grade line for this channel, and under conditions of uniform flow, constant channel cross-section, there'd be an energy grade line here playing the same relationship as it did in Bernoulli's equation. The difference is some velocity hid. And I'm being vague on purpose. Look at a sewer. Sewers are pipes or box culverts, what have you. They have a front and back wall in this drawing as well as a bottom and top component. And if the sewer is flowing part full, so that it has a free surface, then it too behaves as an open channel for the context of this particular class. And there also might be some energy grade line here. Difference between the two is velocity head. If the liquid in the sewer gets up to the top, then it becomes a pipe under pressure, and if there's any additional pressure added, then the hydraulic grade line comes up to the top, and then it keeps going up, and that's a pipe under pressure, and that's was discussed in prior part of the class. Okay, examples of open channels are creeks, ditches, rivers, canals, and sewer pipes that are partially full. Next concept is uniform flow. Uniform flow is the property where the velocity is constant along the streamline. And that would imply that the depth and cross-section are essentially constant. Along the portion of channel, such that the change in velocity with change in x, where x is the flow direction, is 0. That's a uniform flow. In uniform flow, we would have the property that the streamlines are parallel to one another. We generally measure flow depth in this direction. The usual symbol is y. The bottom slope exaggerated in this drawing is S0. The energy grade line, which lies above the hydraulic grade line, so there's our EGL. Its slope, the usual symbol is S sub F. In the case of uniform flow, the energy grade slope, the slope of the hydraulic grade line, and the slope of the channel bottom are all the same. In that instance, this flow depth right here is called the normal depth. And I really don't know the origin of the word normal depth per se, other than it's probably implying that it's measured, it's perpendicular everywhere to the bottom. So that's called the bottom slope. This one is called the energy. And then an older term is called the friction slope. Energy slope, friction slope are interchangeable terms. Non-uniform flow. Well, the velocity varies along the streamline, so let's return to our sketch. of a channel. And make a very exaggerated water surface profile, where this is our hydraulic grade line. So the water, using water, the liquid is all right there. And if we look at two particular points along it, call this one Y1, this one Y2, and it would get me an energy grade line here. Energy grade line is not as curved as implied by the hydraulic grade line, and I don't think I need those. Those are just sections. Okay. A non-uniform flow, imagine if this were a rectangular channel. That's not an absolute requirement, but it makes my story easier to state. If that's the case, certainly from this drawing we can see that Y1 and Y2 are different. So Y1 is not the same as Y2. That would imply, for at least a prismatic cross-section, such as a rectangular channel, that the mean section velocity 1 is not the same as the mean section velocity 2, and that would imply that dV dx, again using that as the x direction, is no longer 0. That's non-uniform. If this happened to also coincide with steady flow, in other words, dq dt was not 0, for this to happen, the only thing we would experience is a convective acceleration term. Apparent acceleration that is a consequence of spatial variation in velocity, but not temporal variation. Temporal variation, as you recall, was called the local acceleration. Like in pipe flow, there's some dimensionless numbers that are important in open channel flow, and I'm just going to state them here without any derivation or development. One of the dimensionless groups that's very important in open channel flow, the name is called the Froude number, and if it's squared, it's essentially, that's Froude number squared can usually be reduced to a mean section velocity squared divided by g times L. That ratio is essentially, I'm using proportional because equality doesn't make sense, to the kinetic forces. Let's just call that over gravity. Now obviously for velocity to become a kinetic force, it has to go from whatever value it is to 0. That can be converted into a dynamic head converting to static head, and we can recover a force. This bottom term is related to the wave speed. And that wave speed is called the celerity. In later classes, when you do detailed studies of open channel flow, a lot of these terms will become more explained to you. Velocity is the mean section velocity. And g is gravitational acceleration. and L is a characteristic length. In our work, usually the depth, but sometimes different characteristic lengths are used. Okay, Reynolds numbers also matter. And the Reynolds number in an open channel is the velocity times a characteristic length called the hydraulic radius divided by the viscosity. R sub h is a hydraulic element called the hydraulic radius. Looks like I'm running out of ink. And it's generally given as the flow area divided by the wetted perimeter. I'm going to declare that pen demised. So color change is only because I needed a pen with ink in it. All right, so that's our dimensionless relations. Froude number, Reynolds number. Hydraulic radius is not a dimensionless thing. It has units of length. It is obtained from the cross-sectional flow area divided by the wetted perimeter. And let's do a sketch to explain three of the important hydraulic variables. Okay. Okay, so imagine, if you will, some sort of channel of arbitrary cross-section here, and sort of a natural-looking channel because I want to illustrate that the geometry controls behavior, but it doesn't have to be a particularly special geometry. So here's our channel, and let's suppose that the water level is right there. From the lowest part of the channel to the water surface is the flow depth, y. The contact point from left to right, and left is always defined by international convention as left looking downstream, so you can imagine that if there's flow, it's headed that way, downstream. That's called the top width. The usual symbol is T. The cross-sectional area is everything I'm shading. That's symbol A for area. And the last one is the wetted perimeter, which I'm going to color in red. It's the only color I have handy. So the wetted perimeter is whatever that length is. Okay, so those are the hydraulic elements, the hydraulic variables. This is called the top width. This is the area. That's the depth. And wetted perimeter. There's a couple more hydraulic variables that sometimes play a role. We're not going to define those until and if we need them for this class. Well, let's look at a couple of common engineering geometries and see what we can learn about these variables. Okay, so the first, actually I think I can pull this off on the same sheet of paper. No, I want to leave the power of video editing. there we go. So there's my definition sketch, and I'll be moving this back and forth. Let's first look at the hydraulic variables. In a rectangular channel. So here's my rectangular channel. It's supposed to be a rectangle. There's my sketch. I'll go ahead and put in wherever my water is. Flow depth is Y. The bottom width, a common symbol for that is B, first letter of the word bottom. Top width is here. And we have a wetted perimeter. And of course, the whole point of one of the points is cross-sectional area. Okay, so just examining that, the area of that rectangle is y times b. So area as a function of depth is equal to by. The top width as a function of depth is basically the constant b. There's one exception: when y goes to 0, there is no top width because there's no water. And the wetted perimeter is a function of y. Well, there's y plus b plus y. So b plus 2y. And if we wanted to algebraically write out the hydraulic radius is defined as area over the wetted perimeter, which is by over b plus 2y. Now, if the channel is wide, that would imply that b is going to be quite a bit bigger than 2y, and that would imply that the hydraulic radius is well approximated by by over b, which is just simply the y. So in relatively wide channels, Mississippi River kind of stuff, if the width is quite a bit bigger than the depth, then the depth itself is a pretty accurate estimator of whatever the computational hydraulic radius is. Okay, so do we get all the pieces on here? Sure enough. Okay, let's look at the next geometry, which is going to be trapezoidal channel. So trapezoidal channels, they look like this. And the trapezoidal is an especially desirable engineered geometry because one of its special cases is the rectangle. Another special case is a triangle. By convention, usually the side slopes are expressed as as the ratio of run to rise. So for every unit of depth in this channel, it moves m units to the right, and here m units to the left. Now these side slopes, they don't have to be the same. I'm doing it the same for this development, but they can be different values. The formulas will naturally change. The flat part of the bottom is given b. Here's our water surface. We now have a top width. It's going to change with depth. Depth is measured from the bottom. We have the flow area, and we have wetted perimeter, which is that length plus that length plus that length. Well, if we start with the area as a function of depth, we have the rectangular part, by, plus we have a triangle my times y here, and a triangle my times y here. And so when we assemble all that, we have y plus b plus my. Now the reason we have my instead of my over 2 is because that triangle plus that triangle just makes another rectangle. Top width as a function of y is b plus, well, there's an my and an my, so 2my. The wetted perimeter as a function of y has the b part plus that hypotenuse plus that hypotenuse. So one of those hypotenuses is y times the square root of 1 plus m squared. So that's the Pythagorean theorem. And there's two of them. So there's our hydraulic elements for the trapezoidal channel. Special cases, b equals 0, then you have a triangle. M equals 0 both sides, then you have a rectangle. So trapezoidal channel hydraulic element hydraulic variable calculations covers 1, 2, 3 major geometries in engineered structure, in engineered channels. All right, one we've been avoiding, but now we'll deal with it. Is our friend the circle. So this could be a sewer pipe. Has a diameter d. There's my free surface. There's the flow depth y. I'm measuring along a perpendicular bisector. Somewhere here is the centroid of the circle. These two rays, each one of them is known to be d over 2 units long. And this angle from ray to ray is alpha. Okay, so the radius is defined as d over 2. Excuse me, this part up here, this distance here is d over 2 minus y. And we can use that to find out properties of that triangle. And we can use that also to find out properties of this sector that's split by that chord. So without proof for the circular channel, we can express the angle as a function of y is equal to 2 times the arc cosine of 1 minus 2y over the diameter. Here's my area. Here's my wetted perimeter. And then we have this top width here, which is from that triangle. Once we have alpha, the remaining terms are quite simple. Area as a function of alpha is b squared over 4, alpha over 2 minus the sine, alpha over 2 cosine, alpha over 2. Top width as a function of alpha is diameter times the sine, alpha over 2. Perimeter as a function of alpha is diameter times alpha over 2. And since alpha is defined in terms of y, then we have all three of the hydraulic variables. Now, you notice in the trapezoid and the circle, I didn't bother to actually write the hydraulic radius. There's no advantage to trying to do the algebra to get into an algebraic form. In practice, what we'll do is we'll calculate an area, we'll calculate a wetted perimeter, take their ratio, declare that the hydraulic radius, and then proceed forward. All right, for doing these actual calculations, I've put together some online tools. I'm going to try to get to those and show you where they are. So if we go to our Moodle site, I should be able to get home. Let me remember how to do that. Dashboard, home, back. Yes, I really want to go back. Go to the toolbox, and it doesn't matter which one we choose. I'm going to choose the upper one because I'm pretty sure it's running. We are now in open channel hydraulics, and here is a calculator for trapezoidal channels. Now it's asking for lengths in feet, slopes as ratios. This doesn't have to be in feet. You could use meters, and the equations don't change. In this particular development, you have a left and right slope. But let's do something that's simple. If we have a 2-foot wide bottom, left slope is, let's do a 1-to-1, so that's 45 degrees. If I make it 1 foot deep, I expect the area to be 2 times 1 plus 3 square feet. And then the other terms will be calculated according to the formulas. Press submit. And the area is 3 square feet, top width is 4, wetted perimeter, hydraulic radius, and hydraulic depth, which we don't think we're going to use in this class. Okay, there's a similar tool for circular conduits. In this case, you enter the diameter and the depth, and it will compute the various ratios for you. So if I make it 1 foot deep and a 2 foot diameter, my alpha should be pi over 2, 1.5 and some change. My flow area should be, pi d squared over 8. So 2 squared is 4. 4 over 8 is a half, so I should get a flow area of pi over 2, I think also 1.5. And sure enough, pi over 2, angle, top width is 2, wetted perimeter is 1 pi, calculated hydraulic radius, and so forth. Now, that you can do in your head, but if you have it something different, the tool comes in handy. And you notice here it says if you make the depth deeper than the diameter, we'll get an error. And so here's the error that you get. In this particular instance, that error simply means it can't do the computation, and the programmer of the online site hasn't trapped that error yet, so it doesn't give you meaningful output. When that happens, go back and see if you've done something just like this. Okay, this concludes this video on open channels, and then we'll pick up next time, or the next one, with the energy equation in an open channel.